In this problem, we're looking at a frame which is made up of members AC and BD. Someone has determined that the critical components are members BD and pin C. We want to make sure that BD does not fail in shear. We want to make sure that the shear stress in pin C does not exceed the ultimate shear strength. Our first goal, therefore, is to figure out first what load is carried by member BD and what shear force is carried by C. Therefore, once we have the shear force, we have the shear stress. That is going to be determined from equilibrium. So what I will do is draw a free body diagram of member AC. And member AC is going to have the applied force P. It will have reaction components there of Cx and Cy. And of course, member BD is 2 force, so its load is going to be carried along the line there of BD. So we'll draw FBD, the force, then along the line which connects B back to D. So to this end, what we will do is first write down a moment equation, and that moment equation is going to be about point B. I got P, it's got a moment arm of L over 2 with a plus sign. We have Cy, it also has a moment arm of L over 2 with a plus sign. And for equilibrium, that says then that the reaction force in Y there at C is exactly equal to the load there at P. The next thing that we need to do is the summation of forces in Y. But before we tackle that, what I want to do is do a little bit of trig. We got this angle that BD makes with AAC. And we can write down the sine of this angle is going to be the opposite, which is h, divided by the hypotenuse, which is h squared plus L over 2 squared. And that number is, for the parameters that are given, that's 4/5. Cosine is going to be the adjacent, which is L over 2, divided by the hypotenuse, h squared plus L over 2 squared. And that number is 3/5. So when I sum forces in Y, I've got minus P. I've got FBD times sine of this angle, which I just found, plus Cy. For equilibrium, therefore, what we have is that the load carried by member BD, that's equal to P minus Cy divided by sine theta. And so what we have here is that that's equal to 5/2. Let me write that over such that we can more easily read that. 5/2 P, like that. And lastly, when we sum forces in X, we've got FBD times cosine theta plus Cx. And for equilibrium, that says then that Cx must be equal to minus FBD cosine, and that is equal to minus 3/5 times FBD, so that will end up being minus 3/2 P. Okay, so we've done what we can with equilibrium, and that's given us what we need because we can easily find the axial stress in BD. That's just the load FBD divided by the cross-sectional area of BD. That is 5/2 P divided by B times T. So that is equal to 5/2 P divided by BT. What we want to do is factor in or give it a factor of safety of 3. The factor of safety here, since we're concerned about failure due to high yielding, is going to be the yield strength divided by the stress sigma BD. And so that's going to be 2/5 BT divided by P sigma Y, the yield strength. From this, we see that the thickness T then is equal to 15 halves of the load P divided by B sigma Y. So that's the answer that we need there for A. This is the minimum thickness that we can have and still maintain at least a factor of safety of 3 for yielding. For part B, let's say that we look at the end view of pin C. So as we look here at the end view here, what we know acting on this is that we have a force there of Cx, or sorry, the force components there of Cx acting in the negative x and Cy like this. We don't really care what Cx and Cy are individually, but what we want to know is what's the resultant force C, because that's the shear force that's carried by that pin. So C obviously is the sum of the squares of Cx and Cy with a square root. So that's going to be equal to 3 halves P squared plus Cy, which we saw was equal to P squared. So the shear force in that, the total reaction force here at the pin, I'll get this right in a bit, is the square root of 13 divided by 2P. Now the actual shear stress is going to be half of that shear force, because this is a double sided shear. So we take that shear force on one face, divide by the area of the cross section, and that's pi d over 2 squared. So that gives me square root of 13 divided by 4 p divided by pi d squared over 4. So that result is square root of 13p divided by pi d squared. We want a factor of safety of 3 also in avoiding failure, because the shear stress has exceeded the ultimate strength in shear. So we say that that ratio then is going to be the ultimate shear strength in the pin in shear divided by the actual shear stress. So that's the given value of tau u divided by, what do we find here, square root of 13p divided by pi d squared. And so that's equal to pi d squared tau u divided by the square root of 13p. From this, we see that the minimum diameter of that pin, therefore, is equal to square root of 3 times square root of 13 divided by pi, the ultimate strength in shear, times p. So this is again the minimum thickness of that, I'm sorry, the minimum diameter of that pin that we can have and still have a factor of safety of 3. Let's go back to what we have done. We began by looking at equilibrium. What we wanted to find first is what's the axial load that's carried by BD, because that's going to be a factor in terms of its design, because that dictates the the axial stress. At C, what we needed to do was find the actual load that's carried by pin C. We found first Cx and Cy, then took the magnitude, and then said, well, being as it's a double-sided pin, one face is going to carry only half of that, and then we put a factor of safety 3 on there to find the minimum diameter there of D.